Okay, good morning. So last time we were starting to talk about the problem of a particle in a spherically symmetric potential that's constant or piecewise constant. So particle mass is going to be called mu, and the potential is going to be piecewise constant and spherical. Okay, and so just to graph what it might look like as a function of r, this is the potential. And it's some constant here, and then it changes to some other constant, and then it might change to some other constant up here, and then back down here. So this is V1, V2, which could be negative, V3, V4. Okay, and then in each region with a constant potential, we define a different wave number, k, to be square root of twice the mass times the difference between the energy and the potential in that region divided by h bar. So this is a wave number. It has units of 1 over distance. And then we're looking for stationary state solutions. Which have the following form. So we're going to label them by the energy, total angular momentum, and z component. And a nice reason to do that is then we know that it separates into a radial wave function, which depends only on the energy and the total angular momentum, and a spherical harmonic, which depends only on the angular things. And the solutions we argued last time are going to be of the following form. Well, we already know what the spherical harmonics are, and the radial wave functions are going to be some constant times a spherical Bessel function of rho plus some other constant times a Neumann Bessel function of rho, where rho is equal to the k value times r. Okay, and so the reason we knew that was true is because we'd already solved the free particle, and all this is the free particle here shifted in energy by the amount of the potential. So we already know what those solutions are too. Okay, and then the constants here are going to be fixed by the boundary conditions. We'll do some examples of that. Okay, the boundary conditions are what happens at each one of the join points here where the potential changes. Now, when one does this, since we're just taking linear combinations of the spherical Bessel and Neumann functions, it often turns out that certain linear combinations are useful. So certain linear combinations are useful. So for example, there are combinations called spherical Hankel functions. And all they are is a certain linear combination of these JLs and NLs. The first one is traditionally called little h with a superscript 1. That means it's the type 1 spherical Hankel function. And it's got a subscript L, so it's different for each value of the angular momentum. And as a function of rho, it's just JL plus I times NL. And then if you look back at how we defined the spherical Bessel functions, this turns out to equal minus I rho to the L times minus 1 over rho to the derivative with respect to rho, L times, acting on e to the I rho over rho. Okay, so what happened is the JLs and the NLs have sines and cosines in them, and by taking this particular complex linear combination, it arranges into an e to the I rho. Okay, and then similar, the other linear combination is just where you take the complex conjugate of that. So that's the second spherical Hankel function. It's just JL of rho minus I NL of rho. And that's I rho to the L, the same combination, minus 1 over rho d by d rho, L, but now acting on e to the minus I rho over rho. So why are these linear combinations useful? It's basically because the first one represents an outgoing spherical wave. And the second one is an incoming spherical wave. So how do we know that? So the reason for why they're outgoing and incoming spherical waves is we can understand as follows. If we take the inner product of the position eigenstate with the time-dependent wave function, or the time-dependent ket, we know that the time dependence is e to the minus I times the energy t over h bar. We know that because these are stationary states. Okay, and then here, when we have e to the I rho, when we take derivatives of that, it's gonna stay as an e to the I rho. So whatever it is, it's gonna be some mess times e to the I k times r. And then there's gonna be a bunch of stuff here. Okay, that's for HL1. Okay, and so what is this position, radial position and time dependent stuff? It's e to the I times some constant times r minus some other constant times time. Okay, and that combination is telling you that this is a wave that's moving outward from the origin, or an outgoing wave. And similarly for the other, for the H2, nothing changes except it's got an opposite dependence on R, and so that's going to be moving the opposite direction. It's going to be an incoming spherical wave. By comparison, JL of rho and NL of rho were like standing waves because they had sines and cosines. Okay, so these linear combinations, when I say they're useful, what they're useful for is we're going to use this one whenever we know that the physical situation should correspond to an outgoing spherical wave. This is much more common than the opposite case. HL2 is relatively rare because that's an incoming spherical wave. For that to be physically relevant, you have to somehow conspire for the physical situation to know that there should be a wave converging on the origin. It's much more common for a wave to be outgoing, where you prepare some state and then you find out that it's sort of escaping from its potential. That's what an outgoing spherical wave would look like. Okay, so that's one set of linear combinations. Another set of linear combinations that's useful occurs if the energy is less than the potential in one of the regions. Okay, so the reason we should go back to this formula, if the energy is less than V sub n, that means this is going to be the square root of a negative number, which means k is going to be imaginary. Okay, so in that situation, then K is imaginary. Okay, and so the solutions are just gotten by taking what we had before and plugging in imaginary values. So it'll be JL IKR and NL of IKR. Okay, or one can write HL1, the Hankel functions of IKR. Actually, I should call these something else. Let's call them kappa. HL2 of I kappa R, where kappa is going to be real. So K here is equal to I times kappa, which is I times the square root of twice the mass, Vn minus E. So notice I've flipped the sign under the square root and brought out the factor of I to compensate. Okay, so it's that over H bar. Okay, and so now if we want to avoid all these i's, we can let rho, instead of being k times r, we can let it be kappa times r. Okay, but then a more convenient basis is to define some linear combinations. Again, before we apply the boundary conditions, we don't know what linear combinations they're going to be anyway. And these are the ones that you get from this are called spherical modified Bessel functions. So there's a bewildering array of these things depending on the situation, depending on the physical situation. I always have to look them up. I can never remember which one is which, but here's what they are. The first one is called, unfortunately, I. That should not be confused with the square root of -1. That's the name of the function. It's got an L subscript. It's a function of rho, and it's defined to be square root of -1, so I to the minus L times the JL of I times rho, which is otherwise known as rho to the L, 1 over rho d by d rho to the L, acting on, now when we plug in the imaginary value, it turns the sign into a hyperbolic sign. So this becomes hyperbolic sine of rho divided by rho. Okay, and recall the hyperbolic sine function is equal to e to the rho minus e to the minus rho over 2. And so if you plug that in for rho equals 0, that is vanishing. And so this is a well-behaved function for rho equals 0. On the other hand, if you plug in rho goes to infinity, then you're exponentially growing and the thing will not be well defined. So that answers the question of what these functions are good for. These are good for rho goes to 0, and they're bad for rho goes to infinity. So if you're in a region that extends out to infinity, you don't want to use these functions. And if your region extends to rho equals 0, or the radius is 0, then it's probably a thing to consider, at least, that it might be useful. Okay, the other one, there's always two linear combinations, is called KL of rho. And that's defined to be minus I to the nth power times the first of the spherical Hankel functions evaluated at I rho, which is rho to the L minus 1 over rho d by d rho to the nth power. But now it's an exponential, but it's e to the minus rho because we plug in the imaginary value over rho. So when is this thing good? This thing's good when rho goes to infinity, because then it's exponentially small, which is well behaved. But it's not good at rho equals 0, because at rho equals 0, this is going to 1, and then we're doing 1 over rho. Okay, and so this is good in the opposite limit. This is good for rho goes to infinity and bad for rho goes to 0. Okay, so all of those linear combinations can be useful depending on the particular situation. So now let's just do an example. The one example we've already done was the example in an infinitely deep well, spherical well. And now we're going to do a finite well. So this is going to be a spherical well, and we're looking for bound states. Okay, and so bound states, so first of all, let's draw what the potential is going to look like. So as a function of r, we're going to have it be a constant negative value inside the well, and then it's going to be 0 as we go off to infinity. So here it's minus v0, and here it's 0. So this is v of r. Okay, and bound states here means that bound states means that the energy is less than the value at infinity, which in this case is 0. So energy less than 0 if v of infinity equals 0, which it is in this case. Okay, so now let's write down the solutions in the proper linear combinations. First of all, let's take the case that r is, and this value right here should be a. That's the radius at which this potential changes. So for r greater than or equal to a, our stationary state, well, first of all, we should define what our k or kappa is. Okay, and in this case, the energy is less than 0, so we should be using kappa. Kappa is going to be square root of minus 2 mu times the energy divided by h bar. And then the wave function corresponding to that is going to be some constant a times the modified spherical Bessel function that's good at infinity, which is KL of kappa r times YLM theta and phi. Okay, so what we've done is we've used that we know in advance that this is going to be a solution, a good solution for r goes to infinity. And so we don't want the other linear combinations. In particular, we don't want the IL modified spherical Bessel function, because that would blow up at infinity. So that's not what we want. So if you didn't know this, you could, of course, just try any two linear combinations of these spherical Bessel functions, plug them in, and then you'd have to apply a boundary condition at infinity that the thing not blow up. And then what you would discover after doing some algebra is that this is the correct linear combination. But what we've done is we've sort of already understood which linear combination to use if you want the function to be well-defined at infinity in this region. And so we've already chosen what's the right linear combination, and we don't have to do that extra step here. Okay, this was for r greater than or equal to a, and now for r less than or equal to a. Okay, now k is equal to the square root of 2 mu e plus v0 over h bar. Okay, and the reason for that is we take the energy and we subtract the potential, but the potential was negative V0, so that's why it's E plus V0 here. Okay, and then the wave function in that region is some different constant times, now the appropriate thing to use is just the ordinary spherical Bessel function, JLKR times a YLM. Okay, and the reason we use that is we know the ordinary spherical Bessel function is the good solution for R goes to 0 when the energy is positive, or when K is real as opposed to imaginary. Okay, and in particular, we don't want the Neumann function, because that would just blow up. If we included it in the linear combination, again, we would eventually find that its coefficient had to be 0. Okay, and so now we've got these two expressions in different regions. And the idea is to match them up at the boundary, which is the point R equals A. Okay, now one thing we can do before doing that is we can note that there's a relationship between K and kappa. Namely, it turns out that if you take K squared and you add kappa squared to it, you get twice the mass times V0 over h bar squared. That's going to be useful in a little bit. And one reason it's useful is that notice the energy doesn't appear there. We're trying to solve for the energy, and so it's useful to note that one combination of these quantities doesn't actually depend on the energy. Okay, so we have our two solutions that we're trying to match up, and let's look for a simple solution with L equals 0. So in fact, we're not even going to do the case where L is not 0. It can be done, it's just more complicated. Okay, so we can summarize what we've learned by saying the radial wave function is equal to, in two different regions. So in one region, it's equal to a constant A times K0 of kappa R, which is equal to A e to the minus kappa R over kappa R. That's for R greater than A, or actually greater than or equal to A. And it's equal to B times J0 of KR, which is otherwise known as B times sine KR over KR for R less than or equal to A. Okay, so what have I done? I've just looked up what are the expressions for the modified spherical Bessel function K0, and it's just this. And for the ordinary spherical Bessel function J0, which is this. And now we just have to match. Okay, so we're going to match at R equals A. And so the equation we get is that A e to the minus kappa A over kappa A times the appropriate YLM, which is 0, 0, because we're doing L equals 0, that has to equal B times sine KA over KA times the same YLM. So that just cancels out, right? This cancels with that. And so we get a nice equation, which says that our constant A times e to the minus kappa A has to equal B times kappa over K times sine K. Okay, so that's an equation we have to solve. And that's in terms of, again, this was the definition of kappa. And this was the definition of K. Okay, and so that's one equation we need to solve, but there's a second equation, and that comes about by matching not just the functions, but their first derivatives. So remember, if the potential is not infinite, you don't just match the wave function, you also match the first derivatives at r equals 0. Okay, and so we have to do d by dr a e to the minus kappa r over kappa r at r equals a is supposed to equal d by dr of b sine kr over kr at r equals a. Okay, this is why we're only doing the L equals 0 case, because if we were doing some higher L case, it would get ugly really fast because these functions would be much more complicated. Okay, but we just have to do the derivatives. So when we do the derivative on the left-hand side, we get a minus e to the minus kappa r over kappa r squared minus e to the minus kappa r over r. All of that evaluated at r equals a. On the right-hand side, we get b times minus sine kr over kr squared plus cosine kr over r. Okay, so I've just applied the product rule there. This is evaluated at r equals a. And then a nice thing happens. Well, it's pretty ugly, but a nice thing happens, which is if I apply the previous boxed formula up here, that actually gets rid of this term. Oops, didn't mean to do that. That gets rid of this term and this term. And so all that's left over is a second equation, which is minus a e to the minus kappa a equals b cosine ka. So that's our second equation that we have to solve. So we've got this equation right here, and we've got this equation right here, and we have to solve them. And so one way to do that is to eliminate a first, solve for a. Okay, so solve for a and eliminate it. Okay, and so what you get when you do that is kappa over k b sine ka equals minus b cosine ka. Now everything's proportional to b, so we can assume b is not 0. If b is 0, then we just have the null ket. So we can cross that out and cross that out. Okay, and so what we get then is that kappa equals minus k cotangent of k times a. So that's an equation that has to be true. And we also have this equation, that k squared plus kappa squared is 2 mu v0 over h bar squared. We had written that down before. So now we have two equations in two unknowns. Okay, so in k and kappa. Unfortunately, they're transcendental equations, which makes them hard. But there's a fortunate aspect of this, which is we've actually already seen exactly these equations before. These are exactly the same equations as for the one-dimensional square well. In the case where we take what we called then L over 2 and replace it by A, and where we only look at the odd parity case. So when we did the one-dimensional square well, there were two different types of equations. One was for even parity, one was for odd parity. Okay, and these are the equations that happened for the odd parity case. So let's just remind ourselves of how the solution worked. To solve these transcendental equations, you let x equals k times a, and y equals kappa times a. Okay, and then the equations become the following. That first of all, x squared plus y squared is a constant, so that's a circle in the xy plane. The constant is 2 mu v naught a squared over h bar squared. Okay, so those are circles, depending on what v0 is. And the other equation is that y is equal to minus x times cotangent of x. Okay, and so now we do a graphical analysis to figure out where the solutions might be. So as a function of x, we're plotting y. And so first let's do the second equation, the y equals minus x cotangent x. So if we mark off here pi over 2 and pi and 3 pi over 2 and so on, these solutions look kind of like this. They go asymptotically up. That's a terrible line. Okay, and then the circles, you could have a circle with a small radius, depending on what V0 is. And there's a circle with a larger radius. Okay, and these are different values of V0. So depending on what the V0 value is, actually V0 and A, you get a different radius of the circle, and then you look for where are the intersections of these two curves, and wherever there's an intersection, that gives you a solution. Okay, and so we've already actually done this numerically, and at least in a few cases. One thing to remark, though, that's a little bit different than the one-dimensional case is that for a solution to occur at all, we need the radius of the circles to be large enough, right? So for example, that's supposed to be a circular arc. If that thing's too small, it will never intersect with this line, and you won't get a solution. So you need its radius to be large enough. You need that the square root of 2 mu v0 a squared over h bar squared should be at least pi over 2 to have a chance of intersecting with this curve. So that has to be greater than or equal to pi over 2. Or you can plug that in, or just rearrange that to get that v0 has to be greater than or equal to pi squared h bar squared over 8 times the mass and the radius squared of the potential. Okay, so recall that the one-dimensional square well always had at least one bound state solution. But this one doesn't. The spherical case does not. Okay, so the 3D, what we've learned is that the 3D square well requires the potential to be deep enough in order to have a bound state solution. And a bound state solution here means, again, that E is less than 0. So that's a general fact. We just did a square well here because a square well is relatively easy to solve, but any potential that you draw in 3 dimensions may not have a bound state solution if it's not deep enough. It has to be deep enough in order to have a solution. Again, it's important that this is talking about bound state solutions because you always will have a solution if the energy is positive, which are unbound states. Okay, but we're not going to talk about those until next semester. Okay, any questions on that so far? All right, so let's do another example. This one won't be piecewise constant, so it will require us to solve another differential equation, and we'll run into yet more special functions. So this is going to be the 3D isotropic harmonic oscillator, which we've already solved, but now we're going to find the bound state solutions in another basis. In particular, we're going to look at the complete set of commuting observables consisting of the Hamiltonian, L squared, and L sub z. Okay, so let's remind ourselves what the Hamiltonian is. The Hamiltonian is px squared plus py squared plus pz squared over twice the mass. So that's invariant under rotations. X and y and z are all equivalent to each other. And now we're adding in a potential, which is 1/2 the mass angular momentum squared times x squared plus y squared plus z squared. Also invariant under rotations, because this is also known as just the radial coordinate squared. Okay, so that Hamiltonian indeed commutes with L squared and L sub z. And that means we are entitled to look for, and therefore we will find, eigenstates that are simultaneous eigenstates of energy, total angular momentum, and z component of angular momentum. So in order to understand what these solutions would look like, let's think about what we know already from the other complete set of commuting observables that we had for this problem. So recall, these are Hamiltonian eigenstates in the complete set of commuting observables, which would be hx, hy, and hz. Okay, just the one-dimensional Hamiltonian for x from that part of the Hamiltonian, and y from there, and z from there. Those three Hamiltonians all commute with each other, and so they form a complete set of commuting observables. And so the states were labeled nx, ny, and nz. There's an integer for each one of those. The energies for those were h bar omega times nx plus ny plus nz, plus 1/2 for each one of them, so plus 3/2. And we even know the degeneracies for these. The degeneracies were n plus 1 times n plus 2 over 2. Okay, so this integer here is called n. So the good thing about this is we already know what the eigenvalues are that we're looking for, and we even know what the degeneracies are. Furthermore, we even know something about the wave functions, because if we look at the wave functions in rectangular coordinates, for example, this is just a product of 3 one-dimensional wave functions. So there's a bunch of stuff here that's constants. And then there's a Hermite polynomial for n sub x, which depended on our rescaled x coordinate, and similarly for y, but it has a different Hermite polynomial, and similarly for z. And then there was the exponential factors, which all arrange themselves into e to the minus x squared plus y squared plus z squared divided by 2b squared. Okay, so remember, b was equal to square root of h bar over mu omega. That's some length scale. And this factor at the end, we notice arranges itself into e to the minus r squared over 2b squared. And now what about the Hermite polynomials? The thing we know about them is that they're polynomials. So this is some big, ugly polynomial in x, y, and z, which makes it a polynomial in the radial coordinate and cosine theta and sine theta and cosine phi and sine phi. So it's got some angular dependence, but what that means is that it's going to be a polynomial in R multiplied by some spherical harmonic. Because we know that we're looking for eigenstates of angular momenta, and they always arrange themselves into YLMs. Okay, so what does that mean for us? In our new complete set of commuting observables, the wave functions we're looking for are equal to some constant. We don't have to worry much about that anyway, because we're going to, at the end, we're just going to adjust that to make this thing have unit norm anyway. So it doesn't matter what the constant is very much. Times some polynomial in R times e to the minus r squared over 2b squared times a YLM. Okay, so even without doing anything within this basis from the old basis, this is what we know. And so our goal here is to evaluate what this is. Because whatever that is, that's what our radial wave function is. These are our R sub NL of R's. Okay, and so that's our goal, is to figure out what those are, and we have to solve the Schrodinger equation for those radial functions, but at least we already know something about them. We know that they have an exponential factor multiplied by a polynomial, and we even know what the exponential factor is. Okay, so that if we do everything correctly, it should arrange itself into that form. All right, so the general differential equation for this sort of situation we've already worked out. Okay, we're going to define, as we did before, the radial coordinate is equal to a new rescaled radial wave function u divided by r. And then this turned out to be minus h bar squared over 2 mu, second derivative of u, plus the potential, which now is 1/2 mu omega squared r squared, plus the centrifugal part, which was L times L plus 1 over r squared, minus the energy, all of that times u is equal to 0. Okay, and we're going to be solving that for every different value of L. All right, so that's our goal. We can make our life a little bit easier by noticing that there's also this exponential factor. So why don't we factor that out and hope that the equation gets simpler if we factor out this exponential that we know is going to be there anyway. Okay, so we are going to write that the u is equal to that exponential factor times yet another variable we'll call y. And then we need the derivatives of u, or the second derivative of u. So second derivative of, or the first derivative of u, we should do first. Okay, so we just have to take the derivative. That's minus r over b squared times y plus dy by dr, e to the minus r squared over 2b squared. And then what we really need is the second derivative. So we have to take a derivative of that, which is minus r over b squared minus ry over b squared plus dy by dr. So I'm applying the product rule here again. Okay, all of these are multiplied by the same exponential factor, of course, because when you take a derivative of an exponential, it just pulls down some factors. Okay, and so now if you plug all that in, the exponential factors being common, they all cancel out multiplicatively. And so you get second derivative with respect to r minus 2r over b squared, first derivative with respect to r, and then e. Actually, I'm going to write this in a different way. I'm going to write it as curly e. I'll explain what that is in a second. Minus 1 over b squared minus L times L plus 1 over r squared, all multiplying by y equals 0. Okay, and that's where curly E is just the rescaled value of the actual energy. So it's 2 mu v squared E over h bar squared, which is otherwise known as 2 times the energy divided by h bar omega. So that's a nice combination because we already know the energy is going to be proportional to h bar omega times a rational number. Okay, so secretly, we already know what the curly E is. We know curly E is actually 2n plus 3, where n is an integer, is 0, 1, 2, 3. But we're going to pretend we don't know that when we solve this, just as a check. Okay, so one last thing we can do is, it's again always a good idea to go to dimensionless variables if you can. And so we're going to let x equals r over b. That makes it dimensionless. So now you have to do another change of variables. But the bonus is that this equation turns into y double prime minus 2xy prime plus curly e minus 1 minus L times L plus 1 over x squared times y equals 0. So that's our differential equation that we're going to start with next time. The prime means a derivative with respect to x now, not a derivative with respect to r. Okay, and so next time we will try to find solutions to this equation. So one thing that we anticipate should happen is that the solutions should be polynomials, because they're polynomials in R, which makes them polynomials in X. Okay, so we will start with that next time. All right, are there any questions on today's lecture? No questions?
I got some questions from the notes.
Okay. All right, well, let me stop the recording if they're not about today's lecture, and we can hit those.